Okay, so everyone, so the next talk is going to be given by Jonathan Luck on the topic of Vlasov-Poisson-Landau, which is in the weakly collisional regime, which is actually a problem I've been interested in before. So let's hear it.
Thank you very much. Let me start by thanking the organizers for having me here. It's too bad that we are not physically in Cambridge, but it's still great to be at this event, which has been really nice so far. And thank you, Jacob, for the introduction. And indeed, a lot of what I'm going to talk about is inspired by work of Jacob, as you will see. And I'll be talking about the Vlasov-Poisson-Landau system, in particular in the regime where the collision, which comes from the Landau part, will be very weak. Okay, and the main result that I'm going to talk about is a joint work with Stanford Chaturvedi, who is a PhD student at Stanford, and also Tuan Nguyen, who is at Penn State. Okay, so let's start. So this is the outline of my talk, so it's perhaps not so informative. So I'll first tell you about the system. So I'll tell you what the Vlasov-Poisson-Landau system is, and I'll tell you the basic thing about the Vlasov-Poisson-Landau system. And then I'll start thinking about the weakly collisional regime, which is the regime when the collision, the Landau, seems to be very weak. So in order to study that, I'll first go to the case where there's no collision at all, which is the Vlasov-Poisson case, and then we'll record some results from there. And then I'll talk about our main result, which is a theorem about the Vlasov-Poisson-Landau system when the collision is very weak but non-zero. Okay, and then I'll tell you something about the proof. Okay, so let's start. So the Vlasov-Poisson-Landau system. So let me just write this down. So I'll think of the one species case. Although, okay, you can think of the two species case, which will be essentially the same. So the system is as follows. So this is my main kinetic equation. Okay, so my equation have two sort of nonlinear term. One is the nonlinear term which has to do with Poisson. Okay, so this is a mean field force. The E is given by this. Okay, and there's another nonlinear term which comes from collision, and this is the Landau part. Okay, so I'll be looking for a solution F to this equation, right? So I'll be thinking about the system on the torus. Okay, so from now on, I fix the torus is my spatial domain, and I'll be looking for a function which is a function of Tx and V. X is in T3, and V, of course, is in R3. Let me write down the, I've written down for you how I compute the mean field electric field, which is with this equation here. And the Landau operator is written down here. So this is an equation written down by Landau in 1936. And what it does is it considers binary interaction of so particles will collide, so but only two of them, and the interaction is via Coulomb interaction, and it looks like this. Okay, so the thing sort of just to keep in mind is that this is first a bilinear thing in F. So okay, so it's a quadratic thing in F, and the top order thing is two derivatives of V in F. So you can think of this as like some elliptic operator, except that, okay, it's a bit more complicated. First, it's nonlinear, and second, it involves some weights here, right? Which is both anisotropic and also degenerate, for instance, at infinity. That's what we see here. Okay. So, right, so this, as I just said, this is captures both a mean field effect and collisional effect exactly by this term and this term. And this is the equation that's used to describe the plasma. And in realistic plasmas, the collision is very, very weak. So this nu will be a parameter that captures how strong the collision is. In realistic situation, nu will be very small, let's say around this number, but I'll really in this talk think of it as very, very small. And I want to understand solutions to this exactly when nu is very small. Okay. So now let's start with, okay, what's the first thing we know about Vlasov-Poisson-Landau system? In fact, we know very little. Well, we know that there's an X theorem, and that might suggest that on a torus, any solution will converge to the global Maxwellians. We don't know that, of course. There are important conditional results concerning that, but really the only sort of global solutions that one knows exist are in the perturbative regime. Okay, so this is the important theorem of Guo. In fact, this was first understood in the case where there's no Poisson. So that is to say that's only the Landau equation. So there's no Poisson part in the equation. And in that case, you can ask the following question. Well, first we know that the global Maxwellian, let's fix the constant to just think about this particular global Maxwellian e to the minus v squared. Well, you know that this is a solution, and this you expect to be an attractor of the dynamics. So now you look at this, and then now you perturb it, okay? And you look at initial data f naught, right, which is close to this in an appropriate sense. Then Guo first proved in 2002 for the Landau equation that you have a global solution, so the solution exists globally in time, and moreover, it converges back to the global Maxwellian. This, okay? And the same turns out also to be true if you add in Poisson, and this is actually a much harder problem, and that was understood 10 years later by Guo, and show exactly the same results. Start with the global Maxwellian, which is a solution, perturb appropriately in suitable norms. Then the solution exists again globally in time, and it again converges back to the Maxwellian. Okay, so this is really the most basic thing we know about a Vlasov-Poisson-Landau system. And okay, remember, I want to think about the weakly collisional regime. So I have a parameter nu, which parameterizes how strong the collision is. Well, this theorem, at least at this point, just says that, well, for any fixed nu, you look at small perturbations. The smallness can depend on nu, and then okay, you would have convergence to the Maxwellian. Okay. Okay. So all of this stuff will then from now on we'll be thinking about in certain suitable perturbative regimes, because this is really the only kind of regime we know that there exists a global solution and we can say something. Okay. So there are other related works. Actually, there are many other related works. So let me just cite a couple. So sorry for that I haven't. So there's the work of Strain and Zhu, who generalized this work with Poisson to the case where you're in R3, not T3. And there's also more recent work of Carapetoso and Mishler, which just concerns the Landau equation, but sort of vastly extended the regime of perturbations that's allowed in this theorem. Okay, so let me not say more about that. Okay, so now let's begin thinking about the weakly collisional regime, right? So I recall we look at the Vlasov-Poisson-Landau, the Landau part. Before that, I have the parameter nu, which I want to think of as very small. So let's, as a very first approximation, take it to be 0. Okay, so remember there used to be nu times QL, right? I take nu to be 0, so then this is 0, and this is just the Vlasov-Poisson system. I can already try to understand the long-time asymptotics here. And as it's well known, for this system, there's a very striking phenomenon discovered again by Landau, right, 10 years after he wrote down the Landau collision operator in 1946. And what he discovered is, if you just think about even just the linearized equation, there's a relaxation mechanism. There's a way to decay, but there's no H theorem here. There's no entropy change, but nonetheless, there's a mechanism that decayed. And this is actually very general. There's a very large class of steady states, let's say a large class of solutions, depending only on V, which are therefore then steady state of this equation, for which you can see this phenomenon of what's called Landau damping. But let's say for the purpose of what we are going to do, we are interested in finally going back to Vlasov-Poisson-Landau, which, okay, we know that the things would converge to global Maxwellian, or at least we are only considering that case. So let's just think of Vlasov-Poisson, right? So the nu equals 0 case, that linearize around this particular kind of steady state. And what Landau observed is even for this system, which there's no collision, there's a mechanism for which E will go to 0. Okay, and how does this mechanism work? Well, this mechanism works by phase mixing. Okay, so exactly what, let me try to sort of draw a picture to convey that. So let's try, this is X, okay, and this is V, and X is on the torus, so therefore this is identified, right? Okay, so this is identified. So now I look at the initial data, right? Let's say that look like this, so some blob. Okay, so what happens, actually you can already see this even for the transport equation, but okay, it's harder to think about this actually for the linearized equation around say. But so let's think for the transport equation. What happens for the transport equation is that, okay, now you start moving, right? You start to flow, and of course if you have positive V, let's say here you move in this way, your negative V you move this way, right? So then after a while you would have moved like that, right? But then after a while, you hit the boundaries and then you wrap around, right? So after a long while, you would then get to a situation where you would wrap around many times, right? You would wrap around many times, right? And what happens now is that you have homogenized. If you now look at an integral on a fixed x, so let's say I integrate here along this line, and this I look at the integral f dv, okay, this thing will converge to a constant, okay. But now, of course, this thing is what feeds into the equation for E, and if it's a constant, then the derivative would kill it. So then this thing actually converges to 0. Okay, so the flow would right. So the flow with the phase mix, so to see something like that, and as a result, E goes to 0. And because E goes to 0, now you go back to the equation, right? Now E goes to 0, so this is gone, and now you see that the solution should converge to a solution to the transport equation. Okay, so in fact, this is what happens, and this is at least for the linearized equation. This is already observed by Landau, exactly that by phase mixing, again, E goes to 0 and F converges to transport. Okay, so for a long time, it's an open and hard problem. What happens in the nonlinear setting, right? So I know that there's such a linear mechanism for relaxation. Well, is it strong enough, for instance, to give me a global solution? Does the global nonlinear solution have the same kind of behavior as the linearized equation? And this was answered in the breakthrough work of Moreau and Villani, now more than a decade ago. And let's again just look at this theorem in the special case where I perturbed around this steady state for the Vlasov-Poisson equation. What the theorem of Moreau and Villani said is the following. It says that, okay, now look at this, and now look at small perturbations of this, but small analytic perturbations. Okay, so as I'll try to explain, it's important to think about this in an analytic topology. So look at small analytic perturbations of this, and what they show is that, well, in fact, the linear relaxation mechanism is strong enough to actually give you a nonlinear solution, and in fact, the nonlinear solution looks like the linear solution in a certain sense. Okay, so the theorem says that the solution, first of all, exists globally in time. You do have a global solution, and moreover, well, you don't necessarily converge back to this. Okay, there's no now entropy to force you back to this. You can actually move to a nearby steady states. Let's say you move to a different x independent function, you move to another function of v, but this convergence is only in the weak topology. Okay, and the thing you converge strongly is just you converge to a solution to transport, as I tried to explain in the previous slide. And moreover, E decays. So this is the Landau damping that tells you that E decays, in fact, exponentially fast. They can do that. Okay, and since then the theorem has been extended, simplified, etc. In particular, their work of Bedrossian, Mahmoudi, and Mahor, which extended this to removing analyticity, replacing it by certain suitable Chevret regularity. And there's a more recent shorter proof of Grenet, Nguyen, and Rodniansky. Okay, so this is sort of the first and most important nonlinear result regarding Landau damping for the Vlasov-Poisson equation. But in this theorem, there is an assumption of analyticity, and or in the later extension, you still need some sort of Chevret assumption. So a natural question to ask is, what happens if I just look at smooth perturbations or just Sobolev perturbations? So that's not really known. If I look at smooth perturbations of this, what to say. However, there is a very interesting work of Bedrossian, very recent, or at least it appears very recently. But
yeah, it's actually from 2000.
Yeah, exactly.
Yeah, it's from 2016.
So maybe yeah, right. Okay. Yeah. So what this says is the following. What this says is that you look at Sobolev space data. Okay. It's slightly hard to state exactly what the statement is. So let me just state it in a vague way, which is a Mahor-Villani type theorem does not hold. Okay. So in this theorem, well, he was not exactly considering e to the minus v squared, but you consider something else, for which also the Mahor-Villani theorem applies, a different kind of background. And he looked at Sobolev space perturbations. And he showed that certain estimate that was proven in the Mahor-Villani theorem, the analogous thing fails here. Okay. And actually, there is something that you can almost describe what happens, why it fails. This has to do with plasma echoes, or one way to think about is you have a resonant interaction of different waves. Okay. What is known, and it's consistent with this result of Bedrossian, is the following thing. If you look at Sobolev data, what you can say is if you look at a perturbation which is of size delta, let's say, so that's small, you can still say that Landau damping would dominate the dynamics, but you can't say that it dominates globally. You can say it dominates the dynamic for a time which is of order delta to minus 1. Okay, so if delta is small, you can go longer, and the longer you go is exactly this much you can go. And the result of Bedrossian show that at least in general, you can't expect to go much further than that. Okay, so that's what happens to Sobolev perturbations. So in particular, when thinking about the new, at least the nu equals 0 case, the regularity is very important. You have very different thing that you get for analytic and Sobolev space perturbations. Okay, so now well, I want to go to the main result, right? So recall the main thing that I want to think about in this talk is really the Vlasov-Poisson-Landau system, which has the collision. But I want to look at the case where the collisional parameter is very small, and we have understood what happens when it's 0. Okay. So let's go back to the Vlasov-Poisson-Landau. That is to say, I come back to this equation, I put back this term in, right? So nu is very, very small, but now I want non-zero. Okay. So recall that in the nu equals 0 case, we have seen that there's Landau damping. Well, first we sort of understood as a linear mechanism, but we also understand that, okay, it can be a nonlinear mechanism, well, globally in time for analytic perturbations, or some long time for Sobolev space perturbations. Well, this should have some effect, or in fact, sort of the whole reason for thinking about that is that one expects that this would have some effects, even when you have collision. But now this effect should be independent of how strong the collision is, right? Because it's there even when nu is 0. Okay, so it's meant to describe a relaxation mechanism at order 1 time, right? When nu is very small. This when nu is small, you would already see some decay, and this kicks in order 1 time. But then the truly global dynamics finally should be determined by this, right? So finally, everything should really converge to the Maxwellian. But this comes in a much longer time scale because there's this nu here, right? For instance, one thing you would imagine, right? Because let's say comparison with because of comparison with the heat equation, I told you that this looks like an elliptic operator in V. So you would think, okay, this is like the heat equation, right, with Laplacian in V. So then if that analogy is correct, then what this says is that the dissipation mechanism coming from the collision should come in a time scale of nu to the -1. Okay, and when nu is small, this is much later than the time scale O of 1, which comes from Landau damping. Okay, so I want to describe this, exactly this, that I have Landau damping, and I also want coming into play in O of 1 time, and I want to see sort of in a much later time, depending on nu, the collisional, the entropic effect come. Okay, so in order to understand this, let us go back to sort of what we already know, which is the stability result of Guo, and rethink now more precisely what Guo's theorem tells us in the new small regime, right? As I told you, one can just easily say, right, from Guo's result that you always have the stability of global Maxwellian. However, the stability would depend on the small parameter nu, right? So if nu is small, it might be that you have to take smaller and smaller perturbation of the global Maxwellian, and I want to understand exactly how it depends, right, in Guo's theorem. Okay, so I go back to this, and let's set my initial data. This is my initial data. Let's already write it as the perturbation of the Maxwellian. So the Maxwellian, I want to write it like this, right? So this is something so as to make sure the linearized operator is nice. Okay, and I want to impose some condition of the initial small f naught, right? These are things which are preserved by the conservation law, so I don't have to think about the final state being a different global Maxwellian. I will then converge to this, right? I want to say everything converge to global Maxwellian. The conservation law together with this will force me to converge to exactly this global Maxwellian. Okay. So what does Guo theorem says in this context, in particular when nu is very small? So Guo's theorem, as it was stated, is for nu equals 1. Okay, but let's not worry about that. Let's just go through the whole proof and see what one gets when nu is small. And one figure out that this is what one gets by repeating the proof, let's say, and putting in this small nu. Is that, well, you have a small epsilon, you have stability, so that if my initial function, first of all, satisfy the conservation law, and second of all, I want it to be small. How small? The smallness has to depend on nu, so this small. So it's order of nu small, so order of epsilon nu. Epsilon is universal, independent of nu. So if it's this small, okay, so if as nu becomes very small, you allow only for smaller and smaller perturbations. Then the theorem of Guo tells you that well, the unique solution will be global in time, and moreover, it converges to the global Maxwellian, right, with the stretch exponential rate. And in fact, you can also try to understand how the rate depends on nu, and the rate is this. Okay, so first you don't get exponential, and this is something characteristic of Landau. Well, we'll hear more about this in Duan's talk later this week. But another thing that's important here, particularly in the case when nu is small, is the time scale is exactly nu to the -1, right? So the variable is nu t, that's the decay. So the characteristic time scale is nu to the -1. Okay. So now I want to understand the nu small regime better. Okay. So what does it mean? I want to now look at this, and I want to say, well, there are actually more things at work than just the entropic effect that has been captured in Guo's result. So the first thing I've already mentioned, sort of, which is phase mixing, right? Landau damping. This is something that already happens when nu equals 0. So I would hope that when nu is small, I would have some extra decay mechanism coming from phase mixing, which gives something that's nu independent, and that should happen in a time which also is nu independent. Okay. And it turns out that one expects another mechanism at work here, and this is sort of best seen in the work of Jacob, which I'll also mention later, which he sees this in a different model. But let me just explain what's the other mechanism that's at work here. Well, so so recall that I have let's go back to the equation, right? The equation, right? So I have a transport part and I have a collision part. Okay, so I know the collision part will give me some dissipation, right? So if I'm naive, I would think, okay, as I try to show the naive statement, I would think that this comes into play at time scale, which is nu to the -1. Okay, but it turns out that actually something else can happen, which is, okay, as long as you are not in the zero Fourier mode for x. Okay, if you have zero Fourier mode for x, then of course this hitting on f is the same as dt hitting on f. Then this really looks like a heat equation. But if it's not, then there is really a transport part. And what does transport equation does? What transport equation does, it moves you into high V frequency, right? This is something that actually is related to phase mixing. If you think in terms of V variable, it moves you into high frequency. Now, if you move into high frequency, remember this is like an elliptic operator, right? If it's so, then if you're in high frequency, it will punish it more. Okay, and it turns out that this combination makes the dissipation faster. The dissipation by the collision is stronger because I have a mechanism that moves into high V frequency, and then I have more dissipation. And this is what happens. So the transfer part moves the solution to high V frequency, enhances the dissipation by the collision, and actually decay would occur at a much faster time. It would occur at nu to the -1/3 instead of nu to the -1. Okay, so at this point, okay, a third may be a bit mysterious, but as I'll say, there's a work of Jacob which considers this in the case of Vlasov-Poisson-Fokker-Planck. And in that case, you can write down really the linearized solution, and once you write down the linearized solution, you can read off, okay, nu to the -1/3 is the correct time scale. Okay, so I want to capture both of these things now in the Vlasov-Poisson-Landau system when nu is very small. Okay, and of course, when I capture both of these things, this gives me more decay, right? If I have more decay, I want to say that things should be more stable. So I want to say if I am able to capture this, not only do I have a better description of the solution, I should be able to consider larger perturbations as well. Right? So remember, in Guo's result, there is something that tells you what's the basin for stability is, which is something of size epsilon nu. And I want to say, well, if I capture more decay mechanism, the phase mixing and the enhanced dissipation, then I can get better than that. Okay, so this is exactly the result with proof. Okay, so again, this is joint work with Chaturvedi and Nguyen, and I go back to this is the equation of Vlasov-Poisson-Landau, and I again write my initial data like this already as a perturbation of the Maxwellian, and I impose the conservation law from the get-go. And now the statement is the following. So the statement is, again, there's some epsilon, so that if I'm small, but now I can do it much bigger. Okay, so instead of O of epsilon mu, I allow for perturbations, which is O of epsilon nu 1/3. Okay, then I already have a global solution. Okay, well, the solution would also converge to the Maxwellian, the global Maxwellian, but in the estimates I prove, I also prove estimates that correspond to enhanced dissipation and Landau damping. Enhanced dissipation meaning that I have decay and timescale of nu to the -1/3. Landau damping meaning I have this new independent decay happening at the time of O of 1. Okay. So let me say this in slightly more precise language. So let's fix n. N has to do with how many derivatives I take, has to do with how fast of Landau damping decay I would finally get. Okay, so this is a related thing. Landau damping is such that if you're more regular, you'll decay faster. Okay, so let's fix this. So I want to say there exists an epsilon such that, again, if f naught, so this is about the perturbations, satisfy the conservation law, and suppose it's small in this order, right? So it's O of epsilon nu 1/3 small. In a Sobolev space, let's say with m plus 5 derivatives, which, okay, I haven't defined here. Then I have a unique solution, and now I want to tell you what I mean by the solution actually sees enhanced dissipation and Landau damping. So these are the estimates I prove. Okay, so I have estimates. Let's say I assume initially I have n plus 5. I prove estimates up to n. Okay, you also have some top order estimates, but then they degenerate in various different senses. Okay, it's complicated state. Let me not say that. Okay, so if I lose a few derivative, I have some clean statement, which is the following. I can say that I look at derivatives, right, of f, and I look at this is not the correct statement. Sorry. Sorry. Okay, well, the good thing about Zoom is I can correct them as I put it here. So I actually have to whenever I take a v derivative, I degenerate the estimates. So I have nu to the 2 beta over 3, and I have nu similarly here. Sorry. Okay, so I can take derivatives. If I take v derivatives, things becomes worse. But the point is that okay, first I have an energy bound in the statement. So the L2 norm, it's still of a similar size, right? So there exists a constant for which this holds, right? So comparable to this, and moreover it decays. Okay, so this is again the same decay rate that you see in Guo's work, right? So this is 2/3. And it happens in the time scale of nu to the -1. Okay, but then there's enhanced dissipation. Enhanced dissipation is the following. So if I remove the 0th mode, so this is my notation for removing the 0th Fourier mode for the x variable. Okay, because as I argued, you only enhance with the non-zero mode because then you see the transport and you move to high v frequency. Okay, so if you remove it, now you look at the same thing. Okay, you have a similar estimate, except now here it decays faster, right, in a certain sense. The decay is in nu 1/3 t. Okay, so the time scale for which it decay is nu to the -1/3, so much faster. For technical reasons, we only get this for 1/3. So for very, very large time, this is the dominant decay rate. But anyways, for intermediate time scale, this is the main decay mechanism for non-zero mode. So this is the enhanced dissipation. And finally, I have Landau damping, right? Remember what Landau damping is? Landau damping is saying is a statement where even in nu equals 0, you have some decay. So here's exactly that. Suppose nu is 0, so you don't see this. Then you have this. Then it says that E decays, right? So it decays with the polynomial rate, has to do with the regularity of the initial data. And you can combine this with, okay, for any small nu, you have this extra decay, which is also with an enhanced rate. But as nu goes to 0, this doesn't change. Okay, so this is the statement that we prove. Okay. So maybe so that I tie everything together, right? Let's recall that because of what Jacob showed, you don't expect to be able to show that you can perturb in, let's say, O of epsilon, right? Because if you have your O of epsilon, right, independent of nu, then okay, seems like you can pass your nu to zero limit, then you get a global solution for the Vlasov-Poisson, which you don't expect with Sobolev space perturbations, right? And in fact, I want to argue that this is sharp. Okay, this is sort of the best you can do. In fact, I then argue it's sort of the argument already Jacob had, which is this is the expected threshold. Why? So remember what Landau, what I know about Sobolev space perturbations and nonlinear Landau damping. I know that in Sobolev space, right? So in Sobolev space, let's write it like that. Sobolev space. If I know that this data, then Landau damping up to t equals O of delta minus 1. Okay, so I am considering now initial data, which is of size this, right? So then this consideration tells me that Landau damping would be the main decay mechanism up to this time. Okay, but this is exactly the time scale for which now you see the enhanced dissipation, the enhanced collisional effect, and that kicks in. So then you have no room, right? So you have this data go up to here. You have Landau damping, and then you have a collisional effect coming in. Okay, so you don't expect to be able to do better than this. Okay, and in fact, you can see from the proof, for instance, if you just try to capture enhanced dissipation, but do not capture Landau damping, say, then you would you can get a threshold which is O of epsilon nu to the 2/3. Okay, so to get 1/3, you capture both effects. Okay, so a lot of this is motivated by work of Jacob, who actually proved almost an identical result, again with this threshold of data, and then you show uniform Landau damping, show convergence to the equilibrium. In fact, there the convergence is actually exponential because it's Fokker-Planck. So what he showed is that he considered the Vlasov-Poisson-Fokker-Planck system, and the difference is we try to understand this for the Landau collision, which is what is used to describe plasma. And what sort of is the key difference? So what's the key new thing compared to Jacob's result? The key new things is that, well, if you look at the Fokker-Planck equation, you can linearize it, and the linearization, I haven't really told you what the rho bar, t bar, and u are, so they are something that has to do with the integrals of f. Let's not worry about them. When you linearize, these are like constants. Because of that, okay, you see the operator looks like Laplacian derivative multiplied by v. These are very nice operator, nice in the sense that you can understand it with the Fourier transform, right? And you can actually therefore then solve explicitly the linearized solution, and you can use that to analyze the solution. The difference in our case is that we look at linearized Landau, and first it's variable coefficient, and second, it's degenerate, as I told you, at infinity, and moreover, the weights are anisotropic, different directions. So you don't know how to analyze this with Fourier transform. So the key new thing is I want to develop a strategy in order to prove this result, to estimate the solution, without writing down explicit representation formulas. Okay, I want to just use estimates. To show this without deriving the estimates with the representation formula. Okay. So in the remaining time, I want to explain to you how this is done, what I even mean by this, and what are the ideas in the proof. Okay. So let's start by telling you sort of what's the general strategy of the proof. So first of all, it's convenient to always now, from now on, think about the difference as what I want to consider, right? So I perturb. So this is my function, which I want to say it's always a perturbation of the global Maxwellian. Okay, so let's just think about this f, and I can write down what f satisfies. Okay, so that's the new equation. Let me not make it complicated. All the collision thing, I just do it schematically. So I have a linear part, right, coming from the linearizing the Landau operator. I call it just LF. So this is the linearized thing. And I have a bunch of nonlinear terms. I just call it gamma FF. Okay. And I'll have terms for the Poisson part after linearizing. I have this thing. Okay. So what's the strategy? So the strategy is, again, remember, I don't want to write down any explicit representation formula. So I want to use energy estimates. Okay. So for the moment, what this is very fake. This is a general word for estimates, L2 estimates that you derive by multiplying the equation by something and integrate by parts. Okay. So the first thing I do is I go back to Guo, right? Because I want to sort of get a result that is more stable than Guo, let's say, with the basin of stability is bigger. So I better first understand that. Okay, so I certainly use Guo, and Guo, in fact, also uses an energy method. Okay. So I first have to look at that, look at all the ingredients there. Okay. But then I have to do things, right? Exactly, I have to modify my energy in order to capture the things I want to capture. The first thing I want to capture is enhanced dissipation. And that will be captured by method for hypocoercivity. So that capture enhanced dissipation. And then I also want to capture Landau damping or phase mixing, right? Which happens at time of 1, and for that I use the commuting vector field method. Commuting vector field method, and thank you to Jacques. We have already seen this in the previous talk, and this to capture, let's say, phase mixing. Okay, but that's not enough. I need another ingredient in this proof, which is coming from the fact that if you look at this equation, right, I can't just think of this as an equation for f, right, with error, because there's a term which is linear in E. Okay, so I do want an independent estimate for E. In fact, I want an estimate for the density, and the density estimate will imply the estimate for E, right? Because E is you can get E. Sorry, you can get E from the density by solving the Poisson's equation. So I want an independent density estimate. Okay, and this is sort of in line of how Landau tried to get Landau damping, and this type of independent density estimate is also, for instance, in the proof of Moholy. Okay, so I have to couple this independent density estimate with the energy estimate to complete the proof. Okay, so now let's get more precise. So let's say I start with energy method, and as I told you, I start with Guo. Okay, so what's energy method? So let's say energy method is the following. I want to find some energy, right, E, so that the derivative is non-positive, then I win. Okay, and in order when I do this, I would generate some positive terms coming from the linearized Landau operator. Right, this should give me something that force me to decay. So I would have to understand sort of. So I generate this good term. I have to understand in this good term exactly what power of mu I get. Okay, that would have to do a lot with what decay I get. And finally, what I want to show is that I get something like this to be non-positive. And in showing this, of course, I have to control the nonlinearity, right? A priori, when I differentiate, I will get some nonlinear term on the right-hand side. And I want to say those nonlinear terms I can control using these type of using these type of norms. Okay, so let's try to build a norm. So let's think of the Guo norms. What is it? So let's think of it just at the lowest order of derivative, because so that's less complicated. So I want to say with energy, so it's an L2 norm. Let's build it with f and derivative of f. Okay. So now you want to choose the constants A, B, and D so that things are good. You can control things, and it turns out that you are sort of forced to choose A and B equals 1. And D to be much smaller. And if you make this choice, then you get nu equals to 1. Okay. If nu equals to 1, this tells you sort of the characteristic time scale is nu to the minus 1, right? Because you're saying that you have some sort of norm, which is nu independent, and you have d by dt would be like nu. So therefore, the time scale is like nu to the minus 1. Okay. So let me try to convince you why somehow you're forced to do this. So I copy this to the next slide. So let's try to understand this. Okay, so suppose I just try to look at this. Okay, I want to understand what I get. Okay, so I go back to my equation, right? So of course there are many terms in the equation, but for now let's just look at what I get from the collision, the linearized collision. Okay, so that would be what generate the d term. So what I get is well, of course this is 2 times in the product the f of d by dt of f, and therefore I know that this is minus 2f LF with a nu plus stuff that, let's say for the moment, are less important. And this, right, this L has no nu in it. This is something that I want to say is similar, comparable to, let's say, minus, the nu is still here, something that looks like dv of f in L2 and f in L2. Okay, so I want to say this is like an elliptic operator, so you should control this. So this is a lie, and that's very important. I'll try to rectify the lie in this next slide. Okay, but this is almost true. Okay. So now, if this is the case, now I want to understand, and I want to say similarly, I have dx, and I get something similar, right? So this is minus nu, and then now I have 2 derivatives, dv dx of f, and so on. Okay. But then why I'm forced to make d much smaller, right? I'm forced to make d much smaller is because of the following. It's because if I go back to the equation, right? And let's say I try to differentiate with d by dv. If I differentiate with d by dv, right, unlike d by dx, right? d by dx, for instance, if you look at this term, it just moves right in. d by dv would hit on here to get a v, okay? So the issue is that I would get the equation, which is dt of f, right? Let's say plus v, and then plus nu lf equals to stuff, but I would have it, I would look at dv, that's what I said, dv, but I would have a term which is minus dx of f. Right? So that's the issue. So now what do I do? So if I look at this guy, L2xv, so I would have again a term which are good, right? So these are good terms, good. Okay, I have to tell you what good terms are. Okay, sorry. So dv squared plus dv, right? And then I would have a term which looks like the inner right. So I multiply this equation by dv, so I would have dv dx, right? dv dx. So let's say Nabla-X. Yeah, that's right. That's Nabla-X, Nabla-B. Okay, so I have a term like this. Okay, so I need to control this. So how do I control this? So of course, for this guy, I want to control this. Well, there's not much I can do. I do Cauchy Schwarz. And then I want to control it, the dv, I would have control with a nu. So I would say this is nu, dv squared, but then I need nu to the minus 1 dx squared. Right. So okay, so because of that, then okay, this is much worse. And in order to combine, so as to I put these together so that I get a get a good term. Well, this I need to be able to control using, for instance, okay, mistakes everywhere. So this is the dx, right? Because I've commuted with x. For instance, I want to control using this term. Okay, so therefore, but this is missing 2 powers of nu, and therefore I want d to be 2 powers of nu more in order to be able to put everything together. Okay, so it's ultimately because of this term that you have to choose this to be nu squared. And now once you choose this, well, you see that the time scale is nu to the -1, right? Because you see that you differentiate the norm, and on the right hand side you see this nu, right? So this is again the time scale is here, so there's eta is 1. Okay, so you see.
Jonathan.
Yes.
It's already 54.
Right. So I have until 3:03, right? Something like that.
I thought we were doing 50-minute talks.
Oh, sorry. Okay. Okay.
So yeah, just try to finish up in the next couple minutes.
Okay.
Yeah.
Okay. Okay. So right. Okay. So this slide just tells you that actually the Guo's energy method is actually quite a bit more complicated. I sort of lied a bit. In particular, I have to handle the fact that the Landau operator is not as nice as I have to handle weights and so on. So you have to put in a bunch of things in order to actually do Guo's result. Okay, so let me just use 2 minutes for each additional idea that I want to say. So first of all, I want to capture enhanced dissipation, and actually the idea is quite simple once you write it down. So this is what's called hypocoercivity, sort of popularized by Villani. This type of estimates already known by Harel and Near. So the point is that I want to look at an energy so that I add a mixed term here. Okay. So if this is suitably chosen, this is still a norm, right? So you can control this by these 2. But now the point is, well, this, when you differentiate this, right? Because when you look at dt of dv, you get a dx. When you differentiate this, you get a good term, okay? And because of that, that allows you to choose things to be much better. So you can choose, let's say, AB to be constant, but D can be nu to the 2/3 instead of nu. And this is the main thing that allows one to say that the characteristic timescale is much better. It's nu to the -1/3. Okay, so let me not say anything more about that. And let me just say, finally, in the energy estimate, I need to also capture phase mixing. Okay, so what's phase mixing? So phase mixing, you can think it's a statement that says, let's say, suppose I have the transport equation. Then if I integrate the solution to the transport equation with some smooth function in V, let's say this particular one that appears, then it converges to a constant. Okay, that's the kind of thing I want to say with the quantitative estimate. And now the point is I want to capture this with the commuting vector field. So this is sort of the vector field that you have already seen in Jacques' talk, right? And it has the property that it commutes well with the transport operator. So in particular, if F is a solution to transport, YF is a solution to transport. Now, there's one thing you can say. Now, the second thing you can say is if you control YF, you actually have a decay estimate for this type of thing for sufficiently smooth phi. And this you can just prove very naively by look at the x derivative, put it in, rewrite dx in terms of y and dv. When you see a dv, you integrate by parts, therefore you get an h1 norm, and that gives you a decay estimate. Right? Once you control y, you get a decay estimate. Okay, and then okay, if you commute y more times, you get more decay estimate. Now the point is, I have collision, which okay, it's hard to explicitly say what I have. So now what it's hard to explicitly write down the solution, but nonetheless, one thing I can say is that if I commute my y with the collision operator, it's something controllable. Okay, so if I commute y with my collision, I get something which I control. Okay, it's a lower order term. So now I just have to understand this for YF, but this I can understand using energy estimate, right? This thing it's complicated, but I know it's sort of coercive in the L2 sense. So I can prove L2 estimate for YF. Now the point is once you control YF, you get phase mixing, right? I don't have to compute anything. I just I just sort of put all this in the commuting factor field. And therefore, even if I have collision, I can also have estimates that give me phase mixing. And as I told you, finally, I have an independent density estimate. But of course, Jacob is already sort of staring at me. So let me just finish here. Thank you very much.
Okay, thanks a lot, Jonathan. Yeah, thanks for the nice talk. I don't know if we have time for questions. Maybe if someone has one really quick question. Okay, so.
Can I have a really quick one?
Yeah.
Yeah, thanks for the talk. It was very nice. I was wondering, like, if the initial data is like is algebraic tree, so like the case where you know Landau damping, are you able to extend this theorem to an epsilon basis of attraction? So like.
I would expect that to be true. Yeah, I can tell you sort of what sort of technically I think it's the main thing that I would be worried about and I should check, which is okay. Because all my estimate is just based on these type of energy, right? So I have to now look at all the energy. I have to understand the more derivative I take, how much faster things grow. And in particular, when I take a lot of derivatives, I have to commute many times with the Landau operator. I have to understand sort of the growth of that. I think that's what I worry about most. But otherwise, I imagine that that to be true. Yeah.
Well, you would somehow have to deal with the plasma echoes, but we can talk about it later. Because we're out of time. This will be a long discussion, right? Because you won't be able to use the collision operator to deal with the plasma echoes anymore. But okay, let's. That's in the density estimates, probably mostly and probably solvable. So let's just move on. Okay, so let's. Yeah. Okay. So let's thank Jonathan again for the very nice talk and the nice results, and we'll come back in about 20 minutes. Okay. Okay. Bye, everyone.
Jonathan, can I ask you a question?
Yes, of course.
Oh, first of all, congratulations. It's a really nice result.
Thank you.
But about the use of hypocoercivity.
Yeah.
So if you sort of compare that to this kind of macro-micro decomposition approach, there's a lot of similarity. In the hypocoercivity, you just work at the level of F, the solution, and for macro-micro decomposition, you split up into the projection of the null space, and the microscopic part is good, and the macroscopic part you have to study more carefully. And you also do this kind of splitting into different terms and choosing the constants carefully. Did you look at that at all? Do you think that that would work, or is there some reason why it might not work?
Yeah. So actually, at first we thought we need to do both.
Okay.
That's what we thought, but then we discovered somehow the hypocoercivity already can sort of replace that.
Okay.
And I think so I think so of course there is some so in the Guo you have some macro micro thing that you have to do.
Yeah.
And I think that's hard to so I think you cannot just do that to get enhanced dissipation. And maybe one philosophical reason is that the enhanced dissipation has to do with the k bigger than k non-zero mode.
Okay.
And it's sort of, if you look at the macro and decompose, I don't know, that it seems complicated.
You get zero modes, but they're zero.
Right, for the macro there's zero. Yeah. So can you see the enhanced?
But you also do this thing where you look at the cross term and you add that in.
That is sort of the, maybe I can share again. Is sort of the key for us that that allows one to move to
This is possible. You could also do something like that with macro and micro, but I don't know. I never thought about it carefully. Okay. So in this way, it was clean and clear how to do it.
Right.
Is
Right.
that, and you can't say and if I'm just trying to clarify and understand, so you're not 100% saying that the other approach wasn't,
Yeah. I'm not. Yeah. I'm not ruling that out. Yeah, certainly.
okay. Okay.
Yeah. But it seems to me, yeah, this is what this is how we see the time scale.
Okay. Thank you.
Sorry, I have another quick question related to
Yeah.
so like if you just consider this the energy norm and you are not interested in proving the Landau damping.
Yeah.
You don't want to prove the Landau damping. Do you? Ah, no, okay, no, because you have the linear term in the energy, so you need the Landau damping.
Right. So actually, okay, that's actually a good point. So you should ask already, because Guo also has that energy, also has that linear term, right? But Guo didn't, right? So
Yes.
Guo also has this term, but he doesn't have doesn't do, let's say, the Landau damping part, doesn't have the independent estimate. So actually, there's a way around this, and that's very clever, but it's quite delicate. It's you can build your energy to include terms which kill off this. So that's one thing that's already in Guo. So I can imagine you can try to do that together with the mixed term. So together with capturing enhanced dissipation, but not capturing Landau damping and phase mixing. You can try to build the proof like that. Okay, I haven't checked everything. I think that works, and I think that would give you something exactly as I was saying. You would get in this instead of this, you would get something weaker because you have less decay. You would get new to the 2/3 by just doing that. Yeah.
But maybe you can also go lower in regularity, like you have n greater or equal than 8, which I understand is probably just to don't take in care of a bunch of constants and stuff like that. But like if you're willing to avoid the Landau damping, probably you can go, I don't know, no, maybe n greater than 1, no, but let's say n greater than 3, something like that.
Yeah, that's true. You can also go lower, right. You can also go lower.
I think you can do n greater than 2.
Yeah,
without
probably,
the Landau damping.
Yeah. Right. Both even have very impressive, very low regularity results.
Thank you for Landau. We didn't.
For Landau, right. That's true for Landau. Yeah.
We didn't try Landau-Poisson. Maybe it works.
Yeah.
So can I ask you? I don't know if you were finished with the other question, but for Jacob's result. So one of the very interesting features of your result is that it's epsilon is independent of nu. I don't know if I understood Jacob's result correctly, but I thought that he took the existence for granted and proved the decay. Is that correct, or did he?
So I think he also gets existence. So I think the statement as far as sort of this high level goes is the same. So he also has
the existence was known before his result, but does he prove there's an epsilon independent of nu?
Yeah. So the epsilon is also So it's exactly So the statement is
okay.
Exactly
Exactly
the same.
the same. Okay.
Yeah.
Thank you.
Sure.
Do you think this would work with the non-exponentially decaying in velocity space perturbation approach, or?
Oh, that I don't know. You mean extending
like the Gualdani-Mishler removal.
Yeah, I don't know. Yeah, that would be interesting. Yeah, certainly.
Okay.
Yeah, I don't know.
Carapasso-Mishler,
Yeah.
Okay.
Yeah, that would be certainly very interesting.
Yeah. Well, thank you.
Sure, of course.
It's even earlier for you. It's impressive.
Right.